Good morning, everyone. It's great to be here. It's great to be back in in-person events. And hello to everyone who's going to be watching this online afterwards. I'm Matheus, and I'm here today to talk a little bit about fibers and other things you'll find in React internals. This is me. You can find me as Y Combinator over the internet, and I'm a senior software engineer at Medallia. And also, I am a mentor in TechLabs Berlin, teaching front-end stuff. Before we start, I do have a disclaimer. So the first one is that React source code is something that's constantly changing. And some of the thoughts you're going to see here are like speculations. And the second thing is that at some points, this talk might sound not like a TLDR. But don't worry, whenever you see like this emoji, it means I know it's a huge content payload. No worries, we're gonna discuss a bit more about after the session. So let's jump to a bit of context on why I'm here talking about that. So it all started 2 years ago when a friend of mine, Bruno, he came up with this proposal to bring algebraic effects into JavaScript. So it was those regular TC39 proposals. And he asked me for feedback. And when I started reading it, I found like a lot of things I had never heard of. So I was like, okay, I got to dig a bit more on those. And then suddenly I saw this huge cloud of terms like algebraic effects, continuations, coroutines, fibers, and etc. And at the same point, I didn't know a lot about them. I knew I had heard of something similar when doing React stuff. So that was the idea for this talk, like to put those in an order that makes some sense and to show how they all piece together in the world of React. So starting with fibers, the way I like to talk about fibers is to bring the example of just a simple regular JavaScript function that adds two numbers. So no magic here. If we think about the stack frame for this function, we would get something like this. So we have a return, we have the function itself, and we have parameters, in this case, the two numbers. And then we have some local variables, some local state, in this case, 4. Now, if we try to model a React component or an element in terms of something similar, we would get a really similar data structure, but instead of our function, we would have the components itself. The return would be this thing that for now, we're going to call fibers. And we do have props, and we have some internal state as well. So we can get to a point where we have fiber architecture, that is this React-specific implementation of a call stack-alike model, where React has full control of scheduling what should be done. And now we have a fiber itself that let's see as a stack frame for this given component. Now we can start abstracting those as units of work. So let's think a bit what happens in our components. So first, once the template goes through the JSX compiler, we end up with a bunch of elements. We know that. So during reconciliation, the data from all of those elements returns from our components is now merged into 3 of different fiber nodes that are going to represent them. Of course, depending on the type of the elements, the framework has to do different stuff. So if it's a function component, it needs to perform something. If it's a class component, something different. If it's a portal, and so on, so on. For example, for suspense, it's another thing. And now we get to a point where we have each element converted into this fiber nodes that describes exactly what kind of work that React needs to do. So that's why we can think of it as a unit of work. And the fact that we have those well-defined units of work make it easier to track this work, to schedule, to abort, to have more control. Okay, now that we can see those as units of work, we can start also visualizing them. For this, I'd like to propose one experiment that is inspecting a a regular element. So let's take this app, for example. It's a really, really simple app. It has a few components, one button that increments and decrements some local state that's using useStateHook. If we inspect the fiber, like if we inspect this element, we'll find a lot of metadata. And I know it's impossible to read. I just wanted to show it's a lot of metadata. And this metadata contains things about the props of those components, the state, what's memoized, what's not, children, sibling, and so on. So it's a lot of metadata. On top of this, we can come up with this piece of code, for example. Here, briefly, what I'm doing is I have an empty JavaScript map, and I'm iterating on my elements, and I'm using some of the metadata we found. In this case, specifically, I want to find siblings and children, and I'm adding those to the map. And now I can copy and paste that exact piece of code into React DevTools. So here I have Twitter open, and I'm inspecting. So I'm going to select any components on the screen. In this case, it was the button. And now I can access it from my JavaScript map. And if I log that, you will see all of that metadata. So for example, the simple piece of code would be like the bare bones for building something to inspect elements like React DevTools. If you're more interested in diving into all of those properties, I would recommend checking this part of React Reconciler. It's called React Internal Types. It is basically the documentation for all of those properties. You have like more than a dozen of them. And another really interesting part is React work tags. Here you will see how React describes each of those parts of work. It can be, for example, as I said, portal, suspense list. For now, the list is like you have 25 different types of work, but it keeps growing. Like a year ago when I checked that, it was less than 20. So you will see this list growing as React adds more feature. Now that we can abstract those as units of work and we can visualize them, we can also start thinking about manipulating them. So I do have this question. Who here has ever heard this word, homochronicity? Nice. So I'll take this really simple example. It's in Clojure, but don't worry. Basically, what I'm doing here is I'm binding 1 to x. I'm assigning this, and now I'm incrementing so that I can get the value 2. The reason why I'm showing this example in Clojure is we can see this code as a list of 3 elements. We have a symbol named let. We have a vector containing other 2 elements, and we have a list, again, with other 2 elements. So the reason is this takes us to the definition where homochronicity is the property of some programming languages, for example, Clojure and other Lisp languages, in which the code used to express the program is written using the data structures of that language. For now, we can abstract as the code we write in the languages. It can be abstracted as the data structures of that language. And why I'm talking about this? Because React elements, as we saw, are basically data, are collections of metadata about something. So just like in Lisp, our components can manipulate their children, for example, and do operations based on their metadata. And this takes us to our next experiment, doing pattern matching React. So let's look at this piece of code. Here we have 3 components, match, with, and otherwise. And what this code is doing is it gets an API response, and then if we have an error from the API, it's going to render this error. But if we have an OK response, we're going to render different things based on what is the response. If that's an image, we render an image. If that's text, we render text, and then we have this default case. This sounds a lot like pattern matching. That is a feature that some programming languages have. And under the hood, these components I showed, they are implemented using, again, elements internal data. So in this case, I'm the type, just so that I can switch from when or with and etc. And this children.toRate, it's an utility from React. And we can build more powerful abstractions on top of that. So here, for example, I'm using suspense and lazy, and I'm checking for the browser support for this API. So what we have here is we are using pattern matching plus those two things, and now we will download, the users are going to download only the bundle for the component that actually matches our condition. And everything because we can manipulate based on elements internal data. If you want to check more about that, it's on GitHub, but it's in really alpha stages. But now we can move to our next thing, coroutines. So I started digging about coroutines when I saw this tweet by Andrew Clark. He's one of the core maintainers of React, and it's an old one. But he said that React suspense would trick people into learning about coroutines. And he was right. So I started digging definitions about that, and I found different definitions. The first one was this thing, that a coroutine is a generator, or a producer, if you will, that can also consume values. So I was like, okay, JavaScript generators can consume values. So by these definitions, they could act as coroutines. Another definition out there, it's a generator that can resolve async values, like async await. And this one definition is also really common in the JavaScript world, because when we had Bluebird, for example, or Cole, when we had those promises implementations, they were basically using generators. And even Bubble under the hood, when it implements promise support, is also doing generators magic under the hood. The last one, but also really interesting, was this definition that it's a generator that can yield with a stack full continuation. And it sounds a lot complicated, but for now, let's think of it in terms as we had deep await in the language, or what we have with suspense, where we can pause the rendering at any depth of our component tree. So just to recap, in Fibers, we have control passed to this scheduler that determines what to run next. And it doesn't have to be React scheduler. It's always at the framework level. So in Node.js, it is the event loop, for example, or in another, it can be also the OS scheduler. Whereas in coroutines, we have control passed to the caller and handled by application code. So that's the difference, the layer where things happens. Now we can move to coroutines in React. So they first appeared when the work on React Fibers, like before 2017, was going as a specific component type. So if you remember that list, I showed the work tags where you have all the different kinds of work that can happen. They had two different components, coroutine components and yield components. And the idea, as opposed to Fibers, was to give people writing React code full control over yielding and assumption. And there's this pull request from back then that's really interesting to see the whole idea behind it, etc. But the thing is that they found a lot of issues trying to optimize that, especially with memoization. And back then they gave up. So per se, coroutines in React no longer exist. But I admit it's going to be fascinating to see what they will come up with in the future. But my favorite part about coroutines in React is to think of the abstractions we can do when relating those to concurrent React. So I don't know if you've seen this talk, but it's one by Dan Abramoff from like 4 years ago. And basically in this talk, he was presenting a lot of challenges when building CPU and IO bound stuff. And it was really, really interesting. And I'd like to build something similar. So let's take this one function. It's called resourceful operation. And the only thing I'm doing is I have this value that's a number, and I iterate up to 1 million. And then I add the results and then return a string containing that. So as you can see, I just want to simulate something that's really heavy on CPU. And now I have a resourceful component that's calling that function. So if we see how this runs, you'll see that as I start typing that, the input stops responding. And yeah, it's basically like this. I cannot type anymore, then I have to wait like a lot of time, and I will be able to type a bit more. And like the whole experience is now like really poor. So how could we address this when building a coroutines-based scheduler? So let's take the same code, but let's make a few changes. So it looks like this now, and the difference is now we have a generator for our resourceful operation, and I added this while true loop, and I know it sounds hacky, but all I want to do now is just that I can use in the beginning of this generator, and now I'm instantiating this scheduler object, and I'm calling this perform unit of work method. Let's see the results. So as you can see, first, it's suspense ready, so the user is going to see something in the meantime it's processing. And the second thing is that the input field is not laggy. So at any point in time, my application is unresponsive, and now the user experience is way better. And that's the whole code for the scheduler thing. Yeah, we cannot cover everything, but the key part is this perform unit of work function, where basically I'm switching between 3 different states: idle, pending, and done. And we have some suspense magic here, throwing promises. And the other thing is that I'm using the next method from my generator. So that's everything. And when you see that, it might sound a lot like we just used transitions. So we just, if you see in React 18, we have used transitions. So the result sounds a lot like the same. Let's check how this is with use transition. So the same code. Now we are calling start transition. And this is the result. So you're going to see it's not like 100% as performant as the coroutines one, but it's also really good. So yes, we just recreated some similar stuff as you have in React 18, but using some coroutines magic. And the whole thing about parallelism in React is that there's no use of walls or workers or anything like this, but we do have this multitasking model that's cooperative. And in this model, we have this one single rendering thread, but this is interruptible, so that the rendering task can be interleaved with other tasks that can also be rendering tasks. So in our example, we would have something like this. We have the original rendering task, and then we had user input, and then we had this higher priority render task that is responding to the user input, and then we resume with the original render task. And the thing is that an update can happen in the background without blocking response to new things. And the good thing is that the scheduler is clever enough to switch to this higher important thing and then resume back the original one. And my favorite part is that it yields the execution back to the main thread every 5 milliseconds. And this is not a magic number. It's just that it's smaller than a single frame, even on 120 FPS devices. So, and another thing is, most of our components don't take longer than that to render. It's not like we are iterating on a daily basis up to 1 million inside our components. So in practice, with React, rendering is interruptible. Just before we move to the next stop, I find it really interesting that coroutines are also out there in our lives as front-enders. So, for example, we know that asynchrony in JavaScript is what we call contagious. So, for example, if any function is async, the function that's calling that should also be async, and so on and so on. So, if you've migrated, for example, from a callback-based API into something that uses promises, suddenly you have async await all over your code. And so, yeah. And the other thing is that asynchronicity in JavaScript isn't free. I mean, it has a cost under the hood. So every asynchronous function has to allocate the callbacks for it, and then store those somewhere, and then take a trip back to the event loop invoking those callbacks. And one really good example to illustrate that is Sass. So I think that many of you know Sass. So basically, Sass has the Sass API has 2 main ways of compiling stuff: sync and async. So the async one became really widely used in practice because it enabled async stuff like the Web Access Loader. But for Node Sass, this was, you couldn't tell the difference because everything was built in C++ anyway, so there is no performance issue. However, in .says, because you are subject to the JavaScript performance asynchrony rules, there was something. And the thing is, it was 2 to 3 times slower than the sync version. And they started using node fibers. It's a package, it's a really popular package to address this so that they could write a sync fast code, just like the sync one, using coroutines from node fibers. This is the package, by the way, but I have to tell that because of a change in V8 last year, it's not available in Node. It doesn't work in Node v16, so it's now deprecated. But just so that you see coroutines out there. And now the last, but also really important part, effect handlers. So when you start Googling about those, you see that effect handlers are this thing that asks the call environment to handle a particular task. So when an effect is used, the nearest handler is called, which allows you to run some code in response to that. And I know it sounds a bit difficult to visualize that, but there's this post by Dan Abramov, also core team member of React, that's called Effect Handlers for the Rest of Us. And he provides a really, really good explanation about those using this code sample. So here, the key thing, we have this function, getName, and then this function, it has this block where it assigns name to this perform thing. This is not real JavaScript, by the way. It's a proposal of what JavaScript would look like as it had effects. So we are performing this thing and we are handling it. And if you think it sounds a lot like throw, try, catch. So instead of throw, you have this perform. Instead of catching an error, you handle an effect, and then you have this resume with that lets you jump back to where you executed the thing. And effect handlers in React showed up through a lot of React histories. So the first one was in the layout algorithm. So when, like years ago, they started experimenting with effect handler structures to change the way how React handles layouting. This is a pull request, by the way, but again, for optimizing issues, it didn't move forward. Fast forward in time, when they were remodeling the context API, if you remember, before React 16.3, they also did draft things based on effect handlers and stopped because of issues memoizing those. But again, it's really nice to see the historical value of it back then. And again, now handling side effects with a component. Sebastian Machbach prepared this proposal again years ago on how he envisioned that effect handlers could be used for doing that. And you will see in this example, it's basically you have a component and it's trying to fetch some API to get what theme should be used in the component using effect handlers. And you see, again, a really seamless structure. So that's basically, you can tell that different members of React at different points of time were experimenting with something really similar and that they wanted to bring that into React. And my favorite part, that is in suspense internals. So who here has ever built any API that is suspense ready, like the API? Okay, cool. So for those who haven't, I would recommend you to check one of it, like React Cache, but it could actually be anything that is suspense ready. And you'll find something like this. You throw promises. And because the component is able to suspend the fiber it is running in, by throwing this promise, which is caught by React and handled. And how does that relate to effect handlers? Because again, we have the same throw, handle, resume pattern, but with some workarounds. So a few conclusions I think we might have from this. First one is React Fiber was this rewrite of React that happened before 2017 with focus on giving more low-level control over scheduling, where you have fibers as this low-level cooperative model to handle execution, and effect algebraic effects as a way to handle those where them and their behavior are independent. The second thing is we can notice that React tries to overcome the lack of those JavaScript features